In this video, we will be covering mass spectroscopy. Here's the periodic table, just a reminder that the average atomic mass is the bottom number, the non-whole number on the AP periodic table. It's rounded to the hundredths place. That is the average atomic mass. So this is an example of a mass spectrum. Notice the relative abundance. That means the percentage of isotopes that have the specific mass is the y-axis, and the actual mass, m/z, means the mass per charge, which we are all of these are neutral atoms. So it's really just the mass is shown on the x-axis. So we can see that the mass, the average atomic mass, must be between 90 and 96 AMU for this element. And it will probably be a lot closer to 90 because over 50% of the elements, of the isotopes, have a mass of 90. So maybe it'll be like somewhere between 90 and 92 would be the average if we take into account that there's a few isotopes that have a mass of 96, a few percentage has a mass of 94, but most have a mass underneath 92. We look at the periodic table. Yttrium has a mass of 88.9. That average atomic mass would be much too low to be represented on this mass spectrum. Zirconium has a mass of 91.22. That means the average would be somewhere around here, which makes sense for this mass spectrum. Okay, we said that the average needs to be between 90 and 96 and much closer to 90 than to 96, maybe around 91 or 92. That works for zirconium. Niobium has an average atomic mass of 92.91, so that's almost an average mass of 93. Now, a lot more of the isotopes, a lot higher percentage of this element has a mass below 93. So the average can't be 93, it must be below 93. And molybdenum and TC have a mass of higher than 93. So in this case, this mass spectrum would represent zirconium. That would be the best answer, with an average mass a little bit larger than 91. And again, 51% has a mass of 90, 11% of all zirconium has a mass of 91, 17% has a mass of 92, 18% has a mass of 94, and 3% has a mass of 96. So if we wanted to calculate this average atomic mass, we would take our percentage and multiply it by our mass. Then we would add it to the percentage times the mass of the next isotope. Then add it to the percentage times the mass of the third isotope, and so on. Remember, the percentage is really a decimal. It says 51%. That means 0.51. And so when I calculate my average atomic mass, I would have 90, because that's the mass of the first isotope, times 0.51. That is the percent abundance of the first isotope, plus 91 times 0.11, plus 92 times 0.17, and so on. Remember, you have to divide each one of these by 100 to convert from a percent into a decimal. So the average atomic mass is a little bit over 91, 91.35. That is the closest. Zirconium is the closest. Zirconium is definitely the best answer. This is a rough average atomic mass, right? This on the periodic table is the exact average atomic mass, but it's hard to figure out the exact percentage based on this graph. We can really only guess to the ones place. That's our uncertainty for the percentages. Okay, here's another example. The mass spectrum of the element antimony is most likely represented by which of the following? So here are 4 examples of mass spectrums. If we look at the periodic table, antimony has an average atomic mass of 121.76. So for this first one, there's only one isotope with exactly a mass of 122. So if antimony's mass was 122.00, this would be the mass spectrum for that. But it's not. Antimony has a mass of 121.76. If we look at the second one, the average atomic mass of this one right here, we have maybe about 30% at 120, 30% at 123, and like 60% at 124 or so. So the average atomic mass would probably be around 123, a little bit higher than 122 at least, because the majority of our isotopes have a mass larger than 122. And notice the mass of antimony is 121.76, so C is not the best answer. If we look at B, we have two isotopes of antimony, one with a mass of 121 and one with a mass of 123. The one with a mass of 121 is slightly higher than the one with a mass of 123. If these two peaks were exactly even, that would mean the average atomic mass would be 122, right in the middle. But since there's a bit more with a mass of 121, the average atomic mass will be slightly less than 122, slightly closer to that 121, maybe around 121.7 or so, 0.8, which matches our average atomic mass. So that's a very good answer. And let's just look at D. D, the vast majority has a mass of 124, probably at least 90%, and then about 5% has a mass of 121 and 120. So that would mean that the average atomic mass of D would probably be like 123.6 or 7. Very, very close to 124, but a little bit less because it does have two isotopes with smaller masses. So in this case, B is definitely the best answer to get us the average atomic mass of 121.76. Here's another example. Potassium has 3 isotopes. The number of neutrons and the natural abundance of these are 20 neutrons at 93.23%, 21 neutrons at 0.012%, and 22 neutrons at 6.73%. Our first step is to calculate the average atomic mass for potassium. Well, we know the average atomic mass should be about 39.10, so hopefully I'll get a number close to that. We also know that potassium has 19 protons. Recall that mass equals the protons plus the neutrons. So here we know every single potassium atom has 19 protons, and then there are 3 isotopes, one with 20 neutrons, one with 21 neutrons, and one with 22 neutrons. So we know that 93% has a mass of 20 plus 19, so a mass of 39 AMU. 0.12% has a mass of 40 AMU from the 21 neutrons plus the 19 protons, and 6.73% has a mass of 41 AMU because we have 22 neutrons and 19 protons. Notice the number of protons is always 19 for potassium. So the average atomic mass would be the mass of the isotope times its percent changed into a decimal plus the mass of the next isotope times its percent changed into a decimal plus the mass of the last isotope times its percent changed into a decimal, and we get 39.17 AMU, which is very close to 39.10 AMU. Again, these won't be exact because the percentages only go to the hundredths place. They don't go as low as they might need to. Some values might be rounded. The next step is to draw the mass spectrum for potassium. So we have our axes, and the y-axis is the percent abundance, and the x-axis is the mass. Our masses range from 39 to 41, so I'll label my x-axis with numbers around 39 to 41. And my percent abundance always goes from 0 to 100, but in this case, it really goes from pretty much 0, from the 0.12 to 93, 94. But there is my label for my y-axis. I know that 93.23% has a mass of 39 AMU, so I'll find 39 AMU on my x-axis and 93-ish% on my y-axis. So that'll be close to around here. And I'll draw my bar. Then I know that 0.12%, so almost 0, but I should have a tiny, tiny bar very low at the bottom, maybe right around here. has a mass of 40 AMU. So I'll draw that bar as small as I can, but to show that that isotope does exist. And lastly, about 7% has a mass of 41 AMU. So I'll draw that bar where like about 7% would be. And that's how you draw a mass spec. You can definitely see from this mass spec that the average atomic mass would be slightly higher than 39, but since most of the isotopes, most of the atoms of potassium have a mass of 39, the average atomic mass should be very, very close to 39. But since a few have a mass greater than 39, the average atomic mass will be a little bit higher than 39.